Let's get started and welcome back. Where we left off on Wednesdays, we had that quiz that was an attempt to look at what is a very common type of question you'll have to be answering as you are building your own single cycle processor or understanding someone else's processor design, which is that connection between the instructions and their functionality, the functional units we have sort of laid out as part of the data path, and how we would generate the control signals for those. I've mentioned enough times that I think the actual module, the control unit, whether it's a single unit or it's a multi-stage unit as the textbook does it, itself is a pretty easy piece of code in terms of lines of VHDL, in terms of debugging that module itself. What is trickier is just making sure you have a good appreciation for how your design all fits together. And the best way I think to do that is just to look at instructions or classes of instructions at a time to get an appreciation for what should those values of the control signals be. And that was the nature of that quiz on Wednesday. We hadn't covered it in that much depth yet. Let's do a few more of those examples today before we move on to secondary topics on single cycle processor design. So this is our diagram, the same as it was on Wednesday. This is your midway through chapter 4 diagram for the single cycle processor. And we know that we have all of these functional elements that we need to implement our single cycle data path. And then we also have the control signals. And those control signals are all being generated by that unit. But maybe more importantly, we can label the control signals with what their value should actually be for a specific instruction. So this is the same exact diagram as before. The title of this slide is the store word instruction and data flow. So the wires are exactly the same here. All we would need to do is annotate them with what should those control signals be. And a poll wouldn't have been a terrible idea, but let's just work our way through a couple of these. I'll use the chat window, and if you know the answer, that's fine. It's not a competition. You're not getting graded on knowing the answer to these. I think what would be important for you is by the end of today, this should be a pretty quick exercise in terms of looking at an instruction and understanding the control signals for that instruction, both in terms of we'll call it the textbook implementation, and then over time, over the next couple of weeks, for your own team's implementation, because the control schemes will be different. Everyone's signals are going to be named somewhat different. Um, the ordering of your muxes is going to then be potentially different as well, and you just have to be the one who has that expertise, expert knowledge. The TAs and myself, we can look at your design, but no one's going to know your design as well as you do, and so you're the one who's really going to have to break down for your control signals what should those values be. So we do this exercise with the textbook version of the data path, and then you extend that for your own purposes for project part B. So if this was a store word instruction, and it always goes back to having a reasonably good understanding of what that instruction is supposed to do. And I know I'm repeating myself a lot here when I talk about, okay, well, a store word instruction is an instruction that takes the base register, adds it to the sign extended immediate offset, treats that as an address, and then writes the second register read value into that memory. That is a store word instruction. You have to know that pretty soon. If you're not there already, you have to have that level of knowledge. It's always fine to have the green card open in front of you. It's always fine and even recommended to have Mars in front of you. Whenever someone posts in Discord, well, what does this instruction do? And for edge cases, I understand people are asking those questions. The most definitive answer for us is always, well, what does the simulator tell us it does? And whether that's correct or not, that's our version of correct for this semester. So based on that understanding of store word, we should be able to, and in this case, as opposed to filling out that table we were doing on Wednesday, we should be able to annotate this diagram very briefly with what we believe the value should be. Some of them are going to be easier than others. So for branch, and this is a signal that we've maybe wanted to call is a branch, or in this design, is a branch equal instruction is probably a better name for that signal, because that's what it is. If you look at this diagram, it is a branch equal instruction only if that signal is high and the output of the computation was 0. Do we set PC source and consequently take the branch target offset? The nice thing about all of that logic in this part of the design is it's kind of sort of irrelevant for us as we're looking at the store word instruction. Store word doesn't have anything to do with branch. We are not branching. right? What about reg write for this design for store word instruction? Reg write, and it's not a bad name. Register file write enable is what that one is doing. Should that be a one or a zero? There's lots of ways we can do this. You have those little buttons where you can click yes or no. Let's see what else you can click. Thumbs up or thumbs down. Well, okay, so we have some disagreement about register write for store word instruction. That's important. Um, what are your thoughts on reg write? I'm asking everyone, not just people who want to type in the chat. Okay, we have some disagreement here. Good, we can battle it out. Click yes if it should be a one, and click no if it should be a zero. I don't know if I can see the results. I think I can. We have one person clicking no. Two, three, four, five. Cool. Is there a way I can then? Where are those on my screen? And I don't think I can show it to you. They are underneath the participants window. So if you open up the window that shows everyone who's in the call right now, you can see those yes and no, go slower, go faster. By the way, feel free to click that at any point. Please go slower. No one ever says please go faster, but feel free to. We have thumbs up. We have waving. That doesn't answer the question. So yes for if that red right signal should be a one, and no if that red white right signal should be a zero. And wave if you just want to say hello. That's fine. And cup of coffee if you need coffee. Okay, excellent. So okay, and we got it. So we don't all have to do it. I'm not taking attendance here. It's nice to get that really quick snap judgment and not kind of depend on the same two or three people typing in the chat window. This may be for yes no questions at least a slightly more efficient way of doing that. So absolutely. So for the store word instruction, and I think I still understand at this point in the semester if you're getting those a little backwards, like which one is store and which one is load. I do understand that, to be honest. Um, for this one though, store word stores to memory, so we do not want to update the register file. Your stuff won't work if you have reg write as one, and it'll actually be a little hard to debug, to be honest with you, because only once you later are using those same registers that happen to be the base address or the right address register for that instruction will you have detected that you updated it to some random value. A little hard to track down. Um, and the truth in debugging these kind of bugs, once you have everything laid out and you're really testing real code, oftentimes it's not the instruction that gives the so-called wrong result. Um, that is the one that's incorrect. It's usually something beforehand that is actually wrong, and you're only seeing the result of it when you have a follow-on instruction that uses that value. So debugging that can be a little tricky, to be honest. So I always say, we want thorough test benches, to thoroughly test our designs. But as we're testing, for example, the store word instruction in isolation, you want to start as simple as possible, right? Start with the most simple, easy to sort of manually, visually debug cases and then add the complexity as you go. You don't want to throw 300 instructions at your test bench. And if everything works, of course, life is good. But when you have a bug, you really don't necessarily know where to start. You'll get that feedback from me a lot when people are asking for help. And I do expect and am looking forward to helping you on debugging these. My feedback will be, well, can you simplify that a little bit? Can you take this really long set of instructions that you have and break it down to, can you find 3 instructions that trigger the problem? And usually the process of finding a good test case is a good part of the way towards actually resolving the problem in the first place. By thinking about what is triggering this error condition, such as the reg write being wrong, you're going to have the solution in the process of doing that. And that's, we say knowing is half the battle, but that's definitely the case for debugging of processor designs. Knowing the right test vector to trigger your bug in as simple a form as possible is a very long part of the way towards resolving the bug. And that you'll find that time and time again. So you'll get that pushback from me sometimes. If you want to send me this massive waveform that has 10,000 instructions and signals in it, and it's going to be really hard to figure out, that'll be my feedback to you. Well, let's trim this down a little bit and figure out what's the least amount of information I need to be able to replicate the bug that I have there. Okay, so that's reg write. What about ALU source? Again, that's another one that we would argue is not named especially well. It's based on the labeling of that mux. ALU input B is reg or immediate or something like that. Would probably be a better name for what ALU source is in this diagram. If it's 0, we take the second read port of the register file as our input to our ALU. If it's a 1, we set the sign extended immediate as our input to the register file. So yes for 1 and no for 0. And click now. The only problem with these polls also, and they're good. I appreciate this as opposed to just one person answering the question, is once there's some momentum towards an answer, it's going to take a lot of guts for someone to click no right now, right? Because, well, 12 people, 13 people have said yes. Uh, this is all for stored word instruction we're doing this one for. Um, but go with what you believe to be the case, because I do want to know if people have the wrong answer for these things. So for all of these for right now, this is for the store word instruction, and that is important. So question is ALU source for the store word instruction, and because we do need that immediate, we're calculating an address that does need to be a 1 for store word there. Yeah, it's in the participants tab. It's not even a poll. It's just to kind of like raise your hand um, / click an icon for yes, no, and we're doing yes for 1 and no for 0 for these cases. Yes, thank you, James. Okay, good. Again, just because 5 people in a row have said 1 doesn't mean it's correct, but I understand that you would feel that would be the case. And you are correct in this case. It is a 1 for ALU source. What about for register destination? So that's a little bit of a subtle mux, right? Different instructions because of the layout of R type versus I type have different places inside that instruction, either the RD field for an R type, or it's actually using the RT field for the I type instructions, have a different place where those 5 bits of write address are encoded in the instruction. It's a pretty subtle feature because we haven't had to really deal with that yet in our labs. The write address has just been an input to our design to this point, so we haven't had to think about it. Register destination is sitting over here on directly below the control unit, and it's not a great name. I'd probably call it RT or RD or something like that is what I would call that. But register destination, it's generally the only place we have to worry about this kind of weird wrinkle of where does that get encoded. The diagram does show it. Is it taking bits 20 down to 16 as our write address, or is it taking bits 15 down to 11 in our write address? I don't expect you to have had that memorized at this point. Because it doesn't matter. Look at the green card for that, or look at Mars for that. You do have to know it, this week in lab, next week in lab, but having that memorized right now. You can think of it, is our format could be a useful control signal to have because it could potentially drive lots of things. That's a design decision that I leave up to your project teams. Do I want to describe the instruction, or do I want to describe the data path functionality in my design as I label my control signals? You got to keep it straight in your mind space. Either one is perfectly fine. But for this one, and we have our poll, 1 for yes, 0 for no, and because I like to be annoying, we'll pull coffee cup symbol. I don't know what that means. Getting coffee, I guess, for don't care. Yeah, okay. I threw that in there after the fact. Yes. I'll be very clear if I ask this on an exam. About the don't care conditions. I'll say explicitly, try to have as many don't cares as possible. From our implementation's perspective, with the synthesis tools being relatively smart enough, the gains of having don't cares in our logic, in our logical expressions, are very nominal, if completely non-existent. But logically, I think it's important for us to appreciate the fact that yes, for the register destination, for a store word instruction, we actually don't care. Okay, before someone tells the joke before I do, it doesn't mean like you don't care about the class. It's you don't care in terms of it could be either. That's another way to think of that don't care result. In VHDL, it's a dash symbol. So you would specify 000-1 or something for the control output for that case. It's probably not even worth it. 0 is fine for this one. being aware that we don't care is what's important, I think, conceptually versus implementation wise. Because we don't care. Because since reg write is 0, we are not writing back to the register file for these store word instructions. By design, we don't care what the address is to our write port. We're not writing anyway. It could be anything. It could be garbage data, and it doesn't really change our processor in any way. That's what we mean. And I think maybe it makes more sense than when you would have learned the same concept in 281, right? It's we don't care. It could be a 1 or it could be a 0. Doesn't matter. That's another way to describe what that symbol would be for this type of design that we're trying to do here. Okay, let's do a couple more. This little polling thing is keeping us all a little bit more awake. Who said it wouldn't be a Friday fun day? Okay, let's see. How about a couple of these? I think by the nature of the instructions we should be on top of. So mem read we've been talking about whether we even need it in our design. This is a textbook thing. We're not reading from memory, so it's either a 0 or a don't care. We don't even have that signal in our designs we're doing. A mem write, I'll give you the answer, is a 1 because that's the whole point of the store word instruction, right? We are writing to memory, so that one does need to be a 1. Final poll question for this store word example. We'll move on to the next one. What about mem to reg? Not a terrible name for the control signal here. Based on the inputs to that mux, it is, do we take the output of the data memory and return that back into the register file? Or do we take the actual output of the ALU and return that back to the register file? That's a yes for 1, a 0 for no, and a coffee cup symbol for don't care. And we got it, right? So there's some disagreement there. The nice thing, I guess, about these don't care answers is in terms of your implementation, you can't get it wrong because we don't care for that one as well. And so whatever you put, your design's never going to be wrong. Um, for this one, right, this mux is again controlling what gets connected to our write data port of our register file. We already, for the same reason as before, know that for this instruction, we're not writing to the register file at all. So who cares? We don't care what's getting written back to the register file. Take the load result from the memory or take the ALU output, which we know is an address and not a value. Doesn't matter. We're not writing it back to the register file anyway, so it doesn't really matter what we do. Cool. Sure. Load word, I think we've covered already, but let's look at branch instead then. I think it's good to do these exercises. We don't need to do 50 of these exercises. Let's do the branch instruction though and lay out those. So that's our branch instruction, which the textbook really just talks about branch equal. Your design will have more complexity in it because you're doing both branch equal and branch not equal. It's just an extra mux, think of our class mascot when you have to design, that part of your implementation there. But the rest of the control signals are important for branches. It is different than the other instructions that we're doing. We'll start with the ones that I think we know off the top of our head, which is, for example, that signal that we decided is called or could be called is branch. Well, okay, I'm telling you this is for branch instruction. That one definitely needs to be a 1, right? That is our branch instruction. The quiz arguably had a pretty serious flaw in it, and I was aware of it and didn't fix it, so assume it was intentional. The quiz on Wednesday asked, what is the value of this signal? But we don't set this signal in our design, right? That's an internal signal that gets generated, right? At least in this design, it is the ANDed output of, if it is a branch instruction with the 0 flag of our ALU, our control unit doesn't set that signal at all. So that the fact that I asked what the value of that should be was slightly misleading and slightly incorrect, I would argue, because it's these red lines that are labeled coming out of the control unit that we're directly setting here. So it's a branch, so we know that that's the case. What about for register write for our branch instruction? For reg write, there's our answer. But for register write, a yes for should it be a 1 and a 0 for should it be a don't write, or a no for don't write for 0 for that case, or something else for don't care for register write. So for this, when I say branch, and when the textbook talks about branch, they're referring to branch equal and or branch not equal. We know there's a few other branch instructions than those, but conditional branches is what this one's talking about. It's not blindingly obvious that that's what this is talking about, but the jump logic's not actually in this diagram yet, and we'll talk about the jump logic and add it to this diagram. The shift left 2 would be kind of the giveaway, to me at least, and only because I've taught this class before. But the shift left logical and added to the PC plus 4, that's our branch target offset. So that signal is corresponding to this mux that's determining whether to take that or to just take PC plus 4 as the next program counter. That's our conditional branch logic in our MIPS. So um, read write and mem write is another good question, Austin. Thank you. Would probably never be don't care. Would certainly never be never be don't care for the write enable signals because we do care. I think always whether or not we're writing to these state elements. When you encode something as a don't care, and I even recommend not even doing just set it as a 0 if you don't want to worry about how to encode the don't care in your VHDL. Um, when you set something as a don't care, you're telling the synthesis tools treat it as either a 0 or a 1, depending on what makes your logic synthesis task easier. Depending on whatever just makes you use fewer gates or use less area or make place and routing different or easier for you. That whole FPGA synthesis tool flow can use those don't cares as part of that, just to make the life a little bit easier. You did that in 281 manually, and it's the same kind of concept that the FPGA or ASIC synthesis tools would allow you to do. So by specifying something like reg write as this is for reg write, as a don't care, you're telling the synthesis tools, well, make it a 0 or a 1, whatever works better for you. But we do care, right? We never want it to be set for 1 if the instruction doesn't require it. So in that case, for those that would, change processor state, and I keep using that term, but writing to resources that then get updated in your processor that you can't undo is another way to think about it. We do care, and so it's never a don't care for that or for memwrite. And so for instructions such as our branch instructions that we know don't write back to the register file and certainly don't write back to memory, that does need to be zeros for that case. Now the other things are nice then though, right? Because we know we don't write back to the register file, it's kind of like the store word instruction in that, well, we don't care what this signal is. Because we're not writing back to the register file, who cares what the actual address is? Likewise, who cares what the actual data that's getting connected back to the register file is? Because we're not writing it anyway. So send whichever data that winds up getting generated in your system. It's garbage. It's incorrect data. It doesn't matter. It's never getting. It's some transient signals that just disappear at the end of that single cycle for that instruction. We do care about ALU source. So that's our final one for the branch instruction here. So for ALU source, let me clear here. For ALU source, should it be a 0 or a 1? So hit yes for 1 and no for 0. Again, ALU source, probably better labeled as use register as second input or use immediate as second input. We have our first close competition. This is exciting. Who's going to win? Now, at this point, I'll note that we did get to 54 participants today, which is wonderful. And people who aren't here who are watching this video offline are having no idea what I'm talking about with regards to hitting yes and hitting no, because none of that is actually getting recorded right now. But I'll take that trade-off. So 18 votes out of 54. That's not how democracy works, people. When I say, register and vote, this is what I'm referring to with regards. So the question is for for the branch instructions still, this is really the last signal that's not decided for us, the value of ALU source. Yeah, okay. The value of ALU source for the branch instruction. And we have a pretty close competition here. So, obviously roughly half of you are wrong, right? Because it's definitely not don't care. We are using the ALU for our branch instructions. we haven't really talked about it that much. I've mentioned it, but we've spent a lot of time talking about load word and store word, and I think less time talking about branch instructions. So the branch instructions, if we're talking about branch equal or branch not equal, right? They take a form something like, branch equal, this just isn't going to work. Branch equal some register value, some other register value, and then some label. Where we do know the label is what's getting encoded as part of that immediate, right? So that's where the label comes into play. It's a PC offset, and we've had some homework questions about that, and you'll have to really know that now as you implement it. There's no denying that. But it's checking equality between registers. If T1 is equal to T2, then branch. And branch not equal is just the exact opposite. So they're doing mathematically roughly the same thing. Check for equality between the two registers that we have specified there. And the implementation strategy we are using, and this is the point I haven't really talked that much about. We brought it up earlier in the semester, but now things are starting to get real with regards to this. Our implementation strategy for branch, at least for the single cycle data path, is use the ALU to determine whether or not two things are equal or not. Reasoning being, we already have the ALU. We spent a couple weeks working very hard on it. We have a capability to determine in our ALU whether or not two things are equal. We have that zero flag, which I hope you've implemented for project part A. It's not hard, but you have to do it if you haven't done it yet because we need it for this purpose. Zero flag is just telling us, was the result of our computation zero, whatever computation we specified. And many processors utilize such a feature. Yeah. Anyway, that's our zero flag. We can do it with big NOR gate. That's one way to determine if the result is all zero. So to implement our branch instruction, one strategy that makes some sense given this existing layout is to treat it like a subtract instruction, in which we don't actually care about the result of the subtraction. We just care if the result of the subtraction was a zero or not. Because if T1 is equal to T2, then T1 minus T2 is equal to zero. And so that's what our branch would be doing here. Take the two registers. So I think that kind of answers the ALU source question. So those of you who put 0 for this were correct. A slim majority. I understand why it's a little tricky. Well, it's a little tricky to draw it here. It's a little tricky because we do need the immediate field for our branch instruction. We do need it. And the diagram does show us using it. We're not using it for the ALU, though. We're not doing any math in the ALU with our immediate field for the branch instruction. That immediate field is likewise going up here. We're treating it like a PC offset, and then we're adding it to the PC plus 4 value via a separate adder that we have in our design. The ALU itself is being utilized to check if the two register values are equal. So we need T1 and we need the value of T1 of T2. So ALU source has to connect to that register file's second output, to do that subtraction equivalent instruction. Not that we care about the result of the subtraction itself, we just care, is the result equal to 0 or not? Did all the two values are they equivalent to each other? You could also do an XOR operation now that we have that supported as well. That resolves any potential overflow issues that may crop up as you're doing branch equals with highly positive and negative values. But either way, you're doing some arithmetic operation that compares the two values bit by bit, and we're checking if the result is 0 or not. And that's how we're implementing our branch instruction. So at this point, as you're working on your own Project Part B implementations, I think it's definitely the case that you'll start to feel, for the class of instructions that you have done already, you have your spreadsheet, you have this laid out, and you're starting to fill out your spreadsheet and implement this for your processor. The trick can be, and this is also why there's going to be a couple of homework questions that are basically doing exactly this, is how do I now add something to this design? Yes, if something is perfectly designed fully 100% and you got it working perfectly the first time, you never need to go through this exercise. But that's usually not going to be the case. And the way I have you work through Project Part B is start with the quote unquote easy instructions or straightforward instructions, then add additional instructions to your implementation. So that's one way we can look at this diagram as well. If we have a working solution here, now let's add the jump instruction to it. And I think that could be a little tricky the first time you do it, because if I were to tell you instead, hey, just implement a jump instruction itself, well, we'd have some questions, but you would know how to do it. It would be okay. Let's recall what the jump instruction is doing. The jump instruction is taking those 26-bit values because it's that J type. It's that J type instruction. It turns it into a 28-bit program counter value, and instead of doing any addition, it just literally replaces the lower 28 bits of the program counter with that encoded 28 bits of a new program counter value. So it's not PC relative, sort of an absolute PC replacement as part of the instruction. It allows you to jump a lot further than what a branch can do for that reason, right? So in isolation, I said, if I were to ask you, think about instruction fetch, how would you implement a jump instruction? Your answer would look, something like this, right? Something like this where you'd have your PC plus 4, and we would have a mux here, right? Where we either take the PC plus 4 value or we take that jump result. But that's not what your challenge is as you're working on project part B here, right? Your challenge is, how do I integrate this with the rest of my design that's already working while supporting both this new instruction and, hopefully, preferably not breaking any of your previous instructions either, right? That's where the challenge comes into play. So it's kind of two aspects of the design you have to keep track of. What do I need for this instruction to work? And what are the correct defaults for all of my controls, that if I'm to add a new control signal, such that I don't break any of my other instructions? So adding a mux is always the answer. But the question is, which mux and where, and how do I control that mux? That's always the case, and that's the framework I want you to be thinking about these problems in terms of. Yeah, we start with the textbook diagram, but you're adding things to that as we go. And in this case, yes, it's adding the logic to do the jump operation, and where we put that logic becomes of importance. So here is a version of the data path that also then includes the jump instruction. And it's starting to get a little messy in the instruction fetch path, obviously. But what we've added is one additional mux. And at least the nice thing about a jump instruction versus some other instructions you'll also have to be adding as you go along here is it is kind of a binary, statically controlled thing, right? It is either a jump instruction or it's not a jump instruction. And if it is a jump instruction, there's not much other decision to be made. It is a jump instruction. That means we take the jump and we're done, right? There's nothing else to it. So in that case, just adding that mux for the next program counter is all we need to really do here. The specific mux that we add, where we put it, what a 0 and a 1 corresponds to, does matter though, in terms of the control scheme for the remainder of your instructions. You can think of it as being a staging where the further along on the signals path you add the mux, the easier it is to kind of overwrite the calculations of the previous instructions you've supported. But that's not a requirement that you do it in such a way. This mux in the textbook implementation, see if I can highlight this a bit better. This mux in the textbook implementation gets added after all the branch stuff. So by default, we're going to take PC plus 4. If it is a branch and it's a branch taken, here's some other mess that we're going to add to it and decide from it instead. But no matter what else happens, if it actually turned out to be a jump instruction, ignore all that, right? Connect all that to the other input of this final mux here, and instead just take whatever our calculation is for the jump instead. We could have done it the other way around, as long as we make sure and have this mux be earlier on in the design, as long as we make sure the values for our other control signals have sane defaults, have correct defaults. So we have to be a little bit careful here, right? So the first part of the answer is straightforward, right? We've added a new instruction, and that's what's going to often happen here, right? You're supporting a new instruction you didn't have before. It's almost always going to require its own new control signal. You can sometimes be clever and support new instructions just via new combinations of existing control signals. You can sometimes do that. It oftentimes isn't even worth it, right? For clarity of your design, we've added a jump instruction. let's add and generate a new control signal called is a jump instruction. And jump is not relative. Jump is an absolute jump that we're doing here. If you look at the spec for it, um, well, it does take the PC plus 4 value and replace it. So if you look at that, it's relative in that sense, but it's replacing. So technically, if our previous instruction was on that 256 megabyte boundary, you'd have that issue. But we're replacing the entire lower 28 bits of our program counter for our jump instruction. But we have this new instruction. We would just add a new control signal specifying it is that type of instruction. And we would just want to make sure that the rest of our signals are reasonable. And the ordering of our muxes can and does matter. Ignoring the other ones like memory write and register write, which we know aren't super relevant for jump, the is branch is potentially relevant or not, right? If if we put our mux for the jump after the mux for the branch, then it doesn't matter, right? Then is branch instruction, I mean, 0 still makes sense, right? Because it is a jump, it's not a branch. But an X, a don't care for the is branch signal, is valid there. Because if you think about how data flows through our system here, it doesn't really matter what is on this line at runtime for our jump instruction. It doesn't matter what's on that line, what's on that signal, what values are on that signal on those wires. Because we're not taking it anyway, right? We're taking the other side of the mux. So that whole path becomes a don't care condition. And so technically, I would say the quote unquote right answer for the control signal for a is branch control when your instruction is a jump is we don't care. We're not taking that logic anyway. However, if you were to implement this in a different way, and there isn't one correct way for it, in which we would have the jump mux first and the branch mux after the fact, and as I call it a jump mux, we have these labels as we do our port mapping in our VHDL. Don't call this label G74 in your design. It's very tempting. This is the 74th mux I've added to my design. That's not going to mean very much to you as you're debugging that, right? Call that something meaningful in our diagram. We haven't been labeling our components in our diagram very much, but you might as well now, right? Label them something that when you look at both the code, when your TA looks at the code, and when you look at the object view of your VHDL, will just be that much quicker to understand what is happening for those, right? In this case, it's a jump mux. Okay, it's the mux that's there to deal with our jump instruction. But what I'm saying here for this final point with regards to the control is the order of those muxes actually does matter. Either one can be fine, but if this jump mux was in fact before the branch mux, then branch could not be a don't care anymore. Branch would have to be a 0 to make sure we're not taking a branch result. We're going to be taking the jump result instead. And so there isn't one right answer for these, but your answers have to be sort of logically consistent with each other in terms of how you're laying out the muxes, and it's always adding a mux. It's just a matter of where, and then what your control signal needs to be for that. So the textbook will say, and when you look at the equivalent part of the textbook where it lays out the control scheme for this, it'll say yes, we've added a new instruction that's going to correspond to a new column almost always in our spreadsheet. And oftentimes, if we have a working design and we're adding a new instruction to it, it's going to be a new column that kind of looks like this quite often, where we have uh, it's a new row for that instruction. We'll have a new control signal with a new column for that new instruction, and it's really only going to be triggered for that new instruction. That'll be a very common thing. People have asked about, load upper immediate instruction. That's probably going to be a separate, row in here and a separate column for is a load upper immediate instruction that's only going to be triggered for that particular instruction. Right? There's other ways you can implement it, but that would be one very common way of doing so. And then the trick is just then for that jump, or for that new instruction, what are the correct results that will not break any of the other instructions? Don't cares are fine if you know what you're doing. If we had put that jump mux before the branch mux, then things like branch would not be an X. It would have to be a 0 for that case. Textbook talks a lot about mem read, but we've discussed that it doesn't really matter for us. You won't even need that in your design. You don't need that column in your implementation. And finally, we have what is now somewhat of an abstract view of the same implementation here, where this is what we've been designing. So we have our instruction memory, which we've kept it as a pretty ideal instruction memory so far. Um, Not worrying about any of the sort of nitty gritty details of how one would actually build such an instruction memory. Same for our data memory. We have our register file, our program counter, and our ALU that we've built. And then we have this control block that is taking the instruction fields and generating all these signals. That is sort of our logical layout of what we're doing, and the rest is just multiplexer details for our implementation. I just want to show you by comparison what that looks like in practice. This is the MIPS R10000. This is not bleeding edge implementation of it, um, but you can look at any modern architectural implementation and look at to the extent that die photographs are either provided or renders of them are provided or people have reverse engineered and done their own analysis of it. And you can start to now map what is happening in the real transistor layout of our chip to what we've been learning so far in this class. Um, we haven't talked about cache yet. It's coming, but that is the messy reality underpinning our idealized instruction and data memories. The rest of this, though, we're not going to be talking about TLB at all. In 308, you should be talking about that as you learn more about operating systems. But the rest of this, and we're not doing floating point at all. This class has got enough complexity in it. But beyond that, this layout does directly correspond to what you've been able to build and what you will be able to build for this project part B going into project part C. It doesn't always correspond to like a nice, neat, logical layout. The layout restrictions of this are based on meeting timing, area constraints, and all the constraints that go into that physical design of the underlying circuit. But there's a direct connection between logically what we're learning and what your old underlying chip winds up looking like. And that's the case for kind of the textbook, sort of not dated, but very traditional MIPS 32 design we're learning. It's the case for the latest and greatest designs released by Intel and AMD and ARM and NVIDIA today. You should always now be able to do that mapping between what their architecture is proposing to have and what we've learned so far in this semester. The remainder is really just details and additional features that have been added up over time, but it hasn't really changed. The core concepts of what underpins a data path for a processor from the early MIPS days, they all still look roughly like this. There's just many, many more transistors to play with, and so many, many more sizes of this and variants of this that you can support inside a single design. As I leave off today, I wanted to bring up one administrative note. It's not meant to be a terribly scary one, but it might be. Our next topic is going to be pipelining. And pipelining is a multi-week topic in this class, and we'll spend a good chunk of the rest of the semester talking about it. But next week we should be able to get to the introduction to what is pipelining, and it's covered in those next sections of the textbook. And I did get the feel, to be brutally honest, some good homework questions people had for homework number 6 and the answers to those. I did get the feel that some of you were asking questions and didn't do the reading first, and I do think a lot of the questions are answered in the reading. The homework questions are textbook questions. We cover some of that in class, but then I do expect you to review that material in the time that you allocate for this course. So when we cover pipelining, we'll start with looking at just those next 2 sections of the book, and then we'll hit that second checkpoint of this semester. So it's already on the class schedule, has been since day one. But start thinking about October 21st, and it's less than 2 weeks from today. We will have our second exam, our second midterm exam, and it's going to cover up through whatever we basically get to on Friday. Homework 5, which was pretty tricky. Homework 6, which I think was more straightforward, and homework 7, which I think you might actually potentially you might enjoy working on that homework to the extent any homework is enjoyable. That's going to really be the basis in terms of the style of questions that will be on that exam. Understanding performance, understanding ALU design, and single cycle architecture. We'll be talking about pipeline architecture in this topic. I don't know how much we'll really be able to get to. Some of the conceptual stuff, the challenging stuff of pipelining will have to happen after that second midterm exam. We'll spend some time in doing a review on that Monday before the exam, but I just want to make sure that's on everyone's calendar as you think about this. This exam should be Easier in the first one. Less of a surprise, I think, in terms of questions and style and proctoring of the exam. And what you're doing in lab is exactly the same thing you're doing on the homework. So the homework is not a waste of time either. It should all kind of all fit together with what you're working on at this middle third of the semester. So let's leave things here for today. I appreciate everyone coming and participating in our polls. Let's try that again. That wasn't terrible. I mean, not every question can break down into yes, no, or coffee cup icon, but we'll try and see what we can do. And try to make some progress on Project Part B, even this weekend if you can. I understand we're all tired and we're all overworked and we're all stressed. But these things, as many of you have noticed, don't lead themselves to late night the night before. It's just hard to cram and get things working and wrestle with the tools at the last hour for this. So get started on it now. Put some effort in now, and it'll really pay dividends for over the next few weeks. Otherwise, I would like everyone, and I hope you would enjoy your weekend. And I will see you all on Monday. Thank you.